In this video, we're going to be doing 2 FRQs for AP Physics 1, Unit 8, fluids, and they're not bad at all, and we'll walk through them. So, a hollow sphere, closed shell of outer radius r and negligible thickness is filled partially with sand, so its total mass is m. The sphere is generally placed in a tank of water and is released from rest. So initially the sphere is fully submerged and then it rises upwards. So we have this tank, and in the tank there's some water. First we have our spherical object on the string and it's above, and then after that you just cut the rope, you just drop it in. So we're said that at first it's fully submerged, but then after this it rises upwards due to a buoyant force that's pushing it back up. So actually there's no string, so we'll remove that. So it just comes back up to the surface. So first we're asked to derive an expression for the initial acceleration that the sphere has immediately after you release the object. So to do part A, we can start with drawing an FBD for our block. So you're gonna have, for your sphere, you're gonna have a wave force that's acting down, and this is gonna stay the same for every single one of these stages. And then you have a buoyant force that is acting upwards. So your buoyant force that is this is for part A. For your buoyant force that's acting upwards, you have FB is equal to the density of your, we're going to say density water, Vg, and we know that the volume, we have to use the volume of a sphere. The volume of the sphere is 4/3 pi times the radius squared, and we know that weight is equal to mass times gravity. So now we can do that the summation of our forces is equal to the mass times acceleration. This is just the same thing as you've done in Unit 1, Unit 2, all the previous units. It's just this time you're just doing it with just FB. It acts the same as just any other type of force. You still have your coordinate system plus x to the right plus y to the upward direction. So you see FB, right? FB points upward, so FB is positive, and you have negative weight, aka mg, because it points downward as usual. You set that equal to your ma. We'll actually say ma here because we're gonna make mass equal to big M. So now all you have to do is replace your FB with what we just defined that FB is over here. So that's gonna be your density of your water times the volume times gravity minus mg is equal to ma. After that, you literally just divide both sides by m, and you can see that that cancels out. So you get that A is equal to this whole expression that we just got minus that mg divided by that m. What you can do now is you see that you have gravity here and you have gravity here. So you can pull that gravity out, and then you can just rewrite this as rho water V over m minus 1. And also, you don't have to pull it out from m in the bottom because that's in the denominator. You're only pulling it out from the numerator, so it's fine. So that's going to be your expression for A. This is an FRQ, so your buoyant force is going to use fluid density, not the object density. Our buoyant force is dependent on what the density of the fluid that you drop the object in is, not what the density of the object that you drop into the fluid. And you also take the volume. You have to find the volume of the object that you dropped into the fluid. So yeah, and you also have your G. Your G is just gonna be your gravitational field strength. Gravitational field strength, which is just 9.8 meters per second squared. So let's do our part B. Our part B says that as the sphere rises, it eventually reaches equilibrium, floating partially submerged. Derive an expression for the fraction of the sphere's volume submerged at equilibrium. So how can we figure this out? Well, we know that we had to first think about what is existing when you have when you have something that is floating at equilibrium. So when it's like just floating there, you know, you're gonna have that FB is equal to mg for your float EQM. Float EQM was what we'll call this. So now, but then after this, we're changing to that only part of the sphere is submerged. So you're gonna have FB is equal to rho, your density of your water times the volume of your submerged part, G. So we can rearrange this. We can just substitute in what we have for FB. So we have, it's the same thing as over there. Okay. So you're gonna have, you can cancel out G on both sides because you see that there. So times M, and then you can divide by your total volume. So you get your V portion that's submerged over V is equal to M over rho V. And that's your final expression. V sub over V, rho of the object over the density of the water, and the object is equal to big M over V. Something to note for here is you want to say that this is V submerged, not the total volume. So let's do our part C. Suppose the sphere is pushed downward slightly and released. Describe whether the motion is simple harmonic motion, overdamped, or something else, and justify. So first, let's talk about what is the condition for simple harmonic motion. That means that you have a net force that is going to be proportional to the displacement from equilibrium. It's going to be linearly proportional. So you have F net is equal to negative K delta Y. This is a linear proportionality because we don't see any squares. We don't see any roots. We just see a linear relationship. Now, what about our restoring force? Our restoring force, when we have our sphere and it's at its equilibrium position, that means that your buoyant force is equal to your weight. Your FB at equilibrium is equal to your mg. So that means that if you push down on your sphere, down with delta y, a small distance, that means, well, you're still going to have your mg, and that's still going to be constant. It's still going to be equal to the weight, but your FB is equal to rho water submerged. G is actually going to increase. That's because more volume is going to be submerged when you push it. And now the net F restoring is going to be the extra buoyancy from our newly submerged volume. So your F restoring now is going to be equal to rho delta V submerged times G. So we have to know that a slice of the sphere is not constant, though. Where our cross-sectional area A is uniform, and also delta V is equal to A delta Y. When you have the sphere, a sphere is going to have a changing cross-sectional area. So for our F restoring, if our force is linear, that means that it's going to be periodic. Or if it's nonlinear, I mean, it's going to be periodic. And it will oscillate, but it won't be simple harmonic motion. So here what we have is that because the F restoring is nonlinear, that means it's not proportional to the displacement. That means it's something else. So, well, if you have your force versus displacement, it's going to be a perfectly straight line in order for it to be Hooke's law. But when you have a vertical cylinder like this, the cross-sectional area is A, cross-sectional area is equal to A, and that's not constant. So because it's not constant because when you push it down, it's going to change. When you push down. So when you push it down, the area changes, and then you get extra FB each centimeter. So that means that your relationship is actually going to be curved like this when you have your F versus X. So this is still going to oscillate though. It's going to oscillate. It's going to go up, or it's going to go, you're going to push it down, right? Then it's going to stop, and then it goes back up, and then it's going to pass EQM, and it's going to repeat. It's still going to be periodic, but it's not sine though. But we know that the force is not going to be linear. It's going to be slightly distorted. It might look like a squash or like a pointy version of the sine graph. So for our floating sphere, that it's non-linear. It's repeating back and forth. It's distorted but non-sinusoidal. And we can technically call this anharmonic. So that was a complicated answer, but you probably won't see something like that on AP Physics, but it's nice to know, have the exposure. So so assume now that the water exerts a drag force proportional to velocity. FD is equal to KY. Determine whether the sphere reaches terminal velocity before it reaches equilibrium, and justify with physics reasoning. So initially you know that you have a force that's going to be acting upward. So that means you have acceleration upwards, and then you have as it rises, like as it's going up, that means that, so as you rise, your V submerged is going to decrease, and then your FB is also going to decrease as a result. Your velocity is going to increase, so as a result your drag is going to increase. So then you get eventually FB is minus mg minus kv is equal to 0. That's the terminal velocity condition. Our equilibrium occurs when FB is equal to mg. So at that point, FB minus mg is equal to 0. So velocity must be 0 at your equilibrium. So that means that the sphere doesn't reach terminal velocity before equilibrium. Because the driving force goes to 0 before the drag balances it. The motion slows naturally. As your FB is gonna decrease. So let's do our second FRQ. Let's take up some room. So let's move this over here a little bit. Okay. So a vertical cylinder is placed in a submerged accelerating elevator that's going up with a constant acceleration of a. The small cube density PC is fully submerged and held at rest by a string attached to the bottom of the container. So first, we know that the pressure is in a accelerating fluid. So if that's the case, you're gonna have fluid with effective gravity. So we can say G effective. G effective is equal to G plus A. So when you're finding your pressure is equal to your P initial plus density, your effective gravity, H. So that's going to be your pressure. You have to include your acceleration. Now, how do you find your buoyant force? Which is going to be the second part. So for buoyant force, this is kind of like what we saw earlier. That's FB is equal to rho V, and that's going to be G plus A. So that's going to be your answer. Now, what's the tension in the string? Should we see here? So for the tension, we have some things that are acting on our cube. In our cube, we're going to have, at the center of mass, you have a weight that is downwards, which is rho C V G, and then you have a buoyant force that's upwards, which is equal to rho V G plus A. You also have the tension that's going to be downward. It's attached to the bottom of the floor, right? So this is that's rho C. So that's the floor, right? This is the tension force. So now we can write our Newton's second law. So summation of our forces is equal to mass times acceleration. We have FB upwards, we have weight downwards, and we have T downwards. That's equal to 0. Now you just substitute in everything. So we already had our buoyant force is equal to that earlier. And we know our weight, which we found for our weight, this is going to be rho C VG. And this is going to be equal to 0. So now you just are going to solve this, or you also have minus T here too. So then you just solve for T. So you would just you would just add T to the other side. T is equal to rho V G plus A minus rho C V G. So that's going to be your answer. Now, okay. After this, we are going to be asked part D. If the elevator's acceleration suddenly becomes 0, describe qualitatively and quantitatively how the tension changes instantaneously. So so what we have is instant acceleration drop to 0. So before, or I'll say initially, you have FB is equal to density V G plus A. Then finally, what you have is your buoyant force is going to be density VG. So what we see is our FB is going to instantly decrease. So our new tension is going to be equal to our density times VG minus density CVG. This is VG times density minus density C. So our change in tension is equal to change in delta T, which is rho VA, density times your volume. So your tension is going to decrease instantly by this amount. That's going to be your answer.